Um, so let's start with our first talk here, and that's by Dominic, Dr. Dominic Widdows. Dominic, are you okay? This is all good. So Dominic, you're still at AMD, right? Correct?
That's right. Yeah.
Yeah. So Dominic works at AMD. He's quite famous for his book on geometry and meaning. And Dominic, you're going to have to correct me. I think, is that still available at University of Chicago Press?
It is. I'm very glad you asked because yes, there's a new book on large language models that I'll talk about as well. But geometry and meaning is still very much available.
Okay. And so he works in quantum computing and software engineering, and is one, I think, Dominic, I could say it. I mean, I think you're the initiator of, with some other people, of the Quantum Interaction Conference series. And so we are extremely happy to have him here amongst us. And Dominic, one thing I have to tell you is that your talk would be recorded. Is that okay with you?
That's fine. Yes, thank you.
Yeah. To the audience too, I think there is a bit of a recording going on here to the audience. Are you all okay with that? Because I had to ask that. So yeah. I presume probably best questions after the talk, I guess, or?
I think probably, but we do have extra time by the sound of things. So if something is really burning right then and you think you might forget it, then yeah, feel free to raise a hand and chime in.
Okay. Dominic, over to you. Thank you.
Right. Thank you very much, Emmanuel. And yeah, very nice to see and hear you. Sorry I can't be there in person, or actually also thankful to modern technology for the ability to have this meeting and interaction with people without traveling so far. So hey, there's a good side to that. But thank you very much to the Fields Institute and to Nathan and the rest of the committee for the work to put this event on. So yes, I'm Dominic Widdows. I work at AMD on profiling chips and machine learning AI models. I've been there for about a year. And this talk is mainly, well, I'll give you a bit of a timeline, but it's mainly based partly on the quantum work I did at Stanford between 2000 and 2004, which led to the book Geometry and Meaning that Emmanuel was so kind to highlight. And then a lot of the more recent work and images, particularly graphics, are taken from papers that I worked on during my time leading the very small AI team at IonQ between 2022 and 2024. And many, well, I think most of this presentation is joint work one way or another, but a lot of work is with Trevor Cohen, and a lot of the more recent work is with Emmanuel Porthos from the City University of London, and Amit Bhattacharya, who is actually an expert in finance and a colleague at IonQ at the time. So thank you to them. All right. So outline of the talk, just so that it really does look like there is a plan. There is a plan. So we've had this question, well, since the 1930s, does quantum physics matter at human scales? And Schrödinger and Heisenberg think some of their writings personify the disagreements there have been over this. And very interesting roots of questions there. And I'll go sort of straight from there to kind of my own view, and very much developed over the last, well, couple of decades working in this area. Like, where is quantum mathematics in AI? And the answer is everywhere. And if there's one theme to my hodgepodge of a career over the past 25 years, I call it baking quantum cakes in classical ovens. There is so much we can take from linear algebra and the related parts of mathematics that we can implement on classical computers that are running like a rocket ship. And there's so much that has been a very fertile area there. And so, yeah. a lot on how did AI get to where we are today, and how do we really build transformer models. And that does lead at the moment to a question on a lot of people's lips. Will quantum computers help? And I will have a plot spoiler. For AI at least, and a lot of any related big data areas, just nowhere close on the I/O requirements. So yeah, there's this quantum mathematics everywhere, but quantum computers are not the right fit of a machine to use it. And then, you know, this is really a finance, and talking about finance and economics, I'd like to talk about what quantum models are the most useful in finance. That's very much a question, because I'm partly hoping that people who know more about this than I do will chime in. But the economic questions for me are very much, I guess, going back to the root of the word oikos, the house, the individual decisions, not necessarily the big macro decisions that we do talk about a lot with hedge funds and very continuous pricing, but the single big decisions like, what house should I move to, or, what school should I try and, get my children to go to? And so some of amongst those quantum models, things on decision making with uncertainty, and talk about some of the recent work that Emmanuel Porthos and I have been doing and talking about group beliefs and group decisions and pricing and volatility. And so that's the outline. Recent timelines. So yeah, it's very nice of Emmanuel to give the introduction, but right now I'm this person working on benchmarking GPUs at advanced micro devices. What's that got to do with quantum? Good question. So I thought I'd start by introducing myself a bit better. Hopefully this also gives people an excuse or reasons to ask different questions later that might not be covered in the talk. And so talking about recent timelines, and I hope it's not too grandiose, that this is a sort of timeline of quantum and AI and machine learning along the top. My own much less significant timeline along the bottom. It's sort of describing how I've felt about the space in recent years, and hopefully it'll help the talk fit together. So sometime in the early 80s, Richard Feynman, the great American physicist, proposed the idea of quantum computers, using some of the ideas of entanglement from Bell's theorem and those results that had become demonstrably real in the 1970s to actually build a computer. And then during the 1990s, I think we still think of this, what still really is the heyday founding of quantum computing, a bit like, say, the 1930s with the work of Alan Turing and Alonzo Church was the conceptual founding of classical computers that were built, reduced to built in practice in the 1940s. Quantum computers have perhaps a longer timeline, being designed in the 1990s and finally, much harder to build, coming to fruition in the 2020s, or at least they're coming online right now. And the great quantum foundations include the design of a quantum computer itself, the logic gates, and the key algorithms that got people excited about this space. So Shor's algorithm for factorizing large composite numbers, Grover's algorithm for a root and search, and so there was big hope in the late 1990s that these would generalize to all sorts of wonderful algorithms we can run on quantum computers. And though Shor's algorithm itself is a very, very specialized thing that works on very small amount of data, like 2048 bits in, 1024 bits out. It's very small. And then in the early 2000s, the web had come along, and big data and machine learning. And by the early 2010s, GPUs were unlocking massive parallelism with neural nets. And by this time, I was involved in computing and having a lot of fun with it. So my own story, no, I wasn't working in quantum computers back in the 1980s, I wish. But I was, busy doing things like rebelling and feeling like I was a teenager who made my own choices. I don't know why have always been so suspicious of classical determinism, but I think it's partly that I started reading about quantum theory during my teenage years, and it really appealed to me. And though I didn't really start working in quantum, my first work at Oxford was in quaternion geometry, actually really useful and fun for quantum computing work later, that single qubit gates are like quaternions. In fact, yeah, I have lots of them on my mug here. I enjoyed designing this mug with quantum gates on them so that I could remember how to program with them. And working with big data and high dimensional vector spaces in the early 2000s, that was my pivot from pure mathematics to computer science and data science and all this stuff that is now part of AI and machine learning. And at the time, latent semantic analysis, word vectors, high dimensional models were not considered part of AI because it was part of, still the AI winter as such, and calling something AI was not a popular term. And then gradually during that last 20 years, we've discovered, oh, no, if you were working on clustering of vectors, we call that AI again now. So like at the time, the work was high dimensional vectors for machine learning and representing concepts. And it gradually became incorporated into this juggernaut of how we do AI today, which I'll be talking about in a moment. So the particularly quantum parts within that, the work on projections, semantic vector products, was a paper delivered at one of those quantum interaction symposia that Emmanuel told us about. So a 2006 paper about using tensor products of vectors and the parallelogram rule for analogies that was probably proposed in numerous places in the late 2010s, but it became very big with Word2Vec and neural networks in the 2013. And by which time Trevor Cohen and I were writing papers on the continuous reasoning, how the combination of tensor products and how that represents entanglement enables us to do symbolic reasoning in vector spaces. And we gathered those results in 2020 in the paper Quantum Mathematics in AI, which you can find in JAIR, the Journal of AI Research. And that was the thing that really, well, it was one of the things that got me involved in the quantum computing community again, and got talking to people at IonQ. And it seemed like 2022 was a really good time for, okay, these machines I've been excited about for decades are really available for developers now. Let's try using those. And so that's what I did for 2.5 years or so at IonQ. I'll tell a bit of the story of that as well. And so in this, does quantum physics affect life? And, going right back to like my time in the early 1980s, I was rather fascinated with this question. And Roger Penrose was talking about it in The Emperor's New Mind, with like ideas that there may be quantum effects going on in the brain. And that's an open question still. And one of the themes of quantum informatics, in the sense like applying quantum to these other fields of life, is we don't necessarily need a causal model of what's going on in the brain and how that applies to decisions right now, any more than we do in other fields of study. So when we use classical economics, we don't have to explain how differentiation within a neuron becomes some sort of differential view of a stock price. We just model the stock price. We don't talk about how it has to come from a model of the human brain. But it's still a really interesting question. And so does quantum physics affect life? And there have been disagreements from well, these books, these disagreements, I'm really talking about what Schrödinger and Heisenberg were writing in the 1950s. You know, they are the grandees, founders of the field by then. If anyone has earned the right to talk about life in general from having studied something in particular detail and the things around it, then yes, the founders of quantum physics. And Schrödinger did not like indeterminism. The notion that Schrodinger's cat was not supposed to be making us think, oh, wow, there's this amazing paradox of a cat in a box. And it was meant to make us think, yeah, that can't really be happening. And Schrödinger, in his book, What is Life, talks a lot about entropy and how big a system has to be entirely predictable, which life needs, and claims that the working of an organism requires exact physical laws. And Heisenberg, who was, along with Bohr in Copenhagen, was a founder of what to this day we call the Copenhagen interpretation of quantum mechanics, reckoned that the translation from the possible to the actual takes place during the act of observation. And so the quantum wave, the wave function, represents a whole collection of potentialities. And the world is in this perpetual state of moving from the potential to the actual, as most of the things that could happen don't happen, and the thing that actually did happen does happen. If any of speaking of those things in terms of tenses in English makes sense. And that the probability function represents a mixture of two things, partly a fact and partly our knowledge of a fact. And this becomes a very interesting question for us in economics and finance. What is a fact? If it's a fact that I paid, $4.50 for a sandwich, then that's a transaction recorded in a book somewhere. It's not a fact that sandwiches cost $4.50. In fact, that probably sounds like a rather cheap sandwich in most expensive cities nowadays. It's a single observation. And how do we generalize those facts? How do we take transactions from the past and think that makes a reasonable value for something similar or equivalent in the future? The facts are made by the previous agreement. It's not inherent to the sandwich that it costs $4.50. It's not an inherent fact to the physics of the sandwich. It's a social fact created about the way we exchange money for the sandwich. So as you can tell, I sympathized with Heisenberg's view from an early age, and that kind of took me into this, I wasn't looking for specifically quantum mathematics and machine learning, but I was definitely predisposed to be very excited when I found it. Actually was told it was there by reviewers. That's another story. So when I keep saying quantum mathematics as distinct from, say, quantum mechanics, what do I actually mean? Well, in quantum mathematics, I mean the state vectors and the Hilbert space formulation of quantum mechanics that was the work of particularly Paul Dirac and John von Neumann in the early 1930s, that we had the wave theory, we had the particle theory, and different approaches to making predictions from these things, indeed from both Schrödinger and Heisenberg, Schrödinger's equation and Heisenberg's uncertainty principle, and come from different approaches to solving the equations of quantum mechanics. And Dirac and von Neumann put them together into what today we call the foundational quantum mechanics. We even talk about the axioms of quantum theory, though you don't really find exact axioms of quantum theory in the works of Dirac and von Neumann. They're sort of abstracted afterwards. So it's not like going to the book of Exodus and finding 2 copies of the 10 Commandments in different chapters and saying, yeah, between those we get the 10 Commandments. It's more like you come to it later and realize, yeah, you can get Dirac and von Neumann's insights down to a comparatively few rules. And those are like state vectors. We represent quantum systems using state vectors in Hilbert space. A Hilbert space is a vector space where infinite sequences, converging series converge, and where there's always a well-defined scalar product. For the purposes of representing information, even in the biggest AI systems, we're always talking about a finite number of dimensions. Even with the exponential growth of memory, addressable memory in quantum computers, we're still talking about a finite number of dimensions. So in practice, a Hilbert space, a finite dimensional Hilbert space, is a vector space with a scalar product. And when you have a vector space, you have projections, and the projections on the vector space correspond to measurements in quantum mechanics. And these are the observations, the state collapse, where the outside interactions with the system, where the term a conscious observer has been used in English for a long time to kind of describe what, well, we don't really know what we mean by a conscious observer in this context, but I will come back to it later. And so the projections in quantum mechanics are always orthogonal to one another. This goes back to the symmetry of the matrices that are operating on the state in the first place. The mathematics of that goes back to Euler's study of rotations in the early and mid 1700s. I mention that because there are beautiful classical results that come from that. I don't know if you can see me throwing things up and down in the air, but if I throw something up in the air and watch it spin and come down, it will spin around three orthogonal fixed axes. Amazing result about physical objects that comes from Euler figuring out that the moment of inertia tensor has to be symmetric. When we're dealing with applications in AI, well, they're not derived from symmetric moment of inertia tensors. It turns out, you can use whatever projections you like, and they often give interesting results. This is one of the many places where the way we use mathematics that was developed and really brought to fruition in quantum mechanics, like quantum logic and the operator theories, like we don't need all of the pieces of that to work in AI. We just need the useful bits. And this goes all the way back to vectors themselves, that Euclid imagined, or the textbook we call Euclid imagines, that you could stretch all ropes to an infinite distance. Well, when you're surveying fields in the Nile Delta, of course you can't. That's an abstraction. It doesn't mean we can't use vectors in situations where they can't be extended to infinity. Like we use vectors with bounded systems the whole time. So when we talk about using quantum mathematics, I think we need to have the same sort of, we take whichever bits are useful. And that definitely includes tensors. And so the tensors come about as linear maps between vector spaces, so operators on vectors. In quantum mechanics, they come about as a representation of the composition of two systems. They're represented in coordinates as matrices, and that's the main usage in AI. They come about as the outer products of vectors. So the inner product of two vectors is like a row vector and a column vector, and you get a number out of them. The outer product is a column vector and a row vector, and you get a matrix. And so you started with two vectors of length n, and you got a matrix of size n squared. Now, obviously, n squared is bigger than 2n for n greater than 2. So as soon as you're dealing with matrices that are bigger than 2 by 2, you can get matrices that are not the outer product of two particular vectors. And just in standard linear algebra, the rank of a matrix corresponds to how many of those products, the minimum number of outer products you need to build the matrix. And that accounts for, mathematically, for what the results that are described as entanglement in quantum mechanics. That's a nice example of where quantum mechanics might be sort of mystical, sound spooky, action at a distance, collapse, but the mathematics behind entanglement is really very simple. So, where is quantum mathematics used? And this really is the stuff I've been working on for, well, 25 years now. Not consistently. It's like it. When I say not consistently, I mean in a bunch of different places, it keeps cropping up. So it was front and center in the work I did at Stanford, and that then vectors have been used in so many places since. It's not really that I've been trying to do quantum mathematics everywhere. It's that it becomes, you couldn't avoid it if you even wanted to. And thinking about it from a quantum point of view can be really helpful. And so let's give some quick examples of that. So yeah, we use vectors throughout in machine learning. I started learning about them as word vectors. We've used word vectors to build information retrieval systems since the early 1960s. It starts with a term document matrix. You count how many times each term occurs in each document. Well, oh, look, you've got a big table. Each of the rows in that table is a vector. And you can do things like take scalar products between the rows in that rows and find the similarity between documents or between terms that way. And you can project those big vector spaces down into smaller vector spaces using principal component analysis. And that became called latent semantic analysis in the late 90s. Turns out that singular value decomposition for principal component analysis, well, that's a lot of computational work to do that. That thing Euler told us to do and was quite right to do with the moment of inertia tensor. And so then we started using random projections because they're computationally much quicker than singular value decomposition and turn out to be really not very much different from in terms of the results you get sometimes. And the use of random projections has gone on throughout machine learning, and we'll come to one of those later. And then we particularly applied projections to ambiguous words. So if you have this vector for, like we took the idea, Romeo comes up a lot in the book we've just written, Large Language Models, Romeo and Juliet. Or Alfa Romeo. Well, one of them's a person, well, a fictitious person, name of a play. The other is a kind of car, probably derived from the Shakespeare name Romeo. You know, maybe the Alfa Romeo is hopefully called Romeo because it's a bit of a heartthrob car, not because it's going to like crash horribly. But yeah, they're different meanings, and we find these meanings by projecting the coordinates. And this was some of the very first work I did in computational linguistics, was asked by a friend doing formal semantics. You can't do negation yet in vector spaces. All you can do is addition and similarity. And I was thinking, well, you've got to be some way of doing negation because we can subtract coordinates. Well, how much do you subtract? Well, enough to make the words you're looking for orthogonal to the words you're not looking for. So in this case, if we take the scalar product of Romeo and Shakespeare, remove that, so we're dropping a perpendicular to this vector we've called Vx, then we get a vector that turns out to correspond pretty closely to the Romeo meaning of sports car. And how did we demonstrate this? What do we mean by it represents this? Well, we do things like finding the nearest neighbor of the projected vector and find that, oh, it's all other kinds of cars now. And so this is an example of quantum logic. The projections are the observation operators, and when you have combination of different possible answers, like maybe it's Romeo or Juliet, then we don't project to just two individual lines like the lines A and B in the bottom left corner here. We project to the subspace that is spanned by those lines. So that point P in the diagram is in the disjunction of A and B without being along the line of A or along the line of B. This, in logical terms, means that quantum logic, the logic that we get by taking points and projecting them onto subspaces, is a non-distributive logic. And there are examples of us using words in non-distributive fashions in real life, like it's 30 or 40 miles, it's say 42 miles from London to Oxford. So if we say it's 42 to 50 miles, yeah, we're in the right range. But if we say get bus 40 or 50 to get there and you get on bus number 42, then you're probably going to go to the wrong place. So distances use something more like a continuous quantum logic, and bus numbers use something more like a discrete Boolean logic. And many more examples like that. Though, like as you get more into logic and language, we find quite quickly that the standard Boolean interpretation of logical connectives is just one of many interpretations. For example, Romeo and Juliet is not the intersection of Romeo and Juliet, it's the disjunction of Romeo and Juliet in this context. And so parts of this mathematics became gradually recognized in AI. In fact, nearly all of it by now is just not called quantum. So by the early 2000s, it was becoming a very standard formulation of statistical AI to talk about learning in terms of a data set of feature vectors, X, maybe corresponding labels, Y. Generative models learn new combinations of X, Y. Classification models just learn a Y given an X. In all of these cases, the X is a vector. We don't worry about whether it can be extended to infinity or any of those other Euclidean axioms. We just assume the ones that are useful to us and carry on from there. And it works very well. And by the early 2010s, the field was really getting excited about tensors as well. This really happened in natural language processing with Word2Vec and then fast text. The neural net training of word vector models that really kicked off around 2012, 2013. And so these word embedding models, the word vectors that we'd been building for years by then, were superseded very quickly by neural word embeddings. And so you learn the coordinates not by random projection, not by singular value composition, but by having input and output vectors, a layer of neurons in the middle, and training that network to maximize the similarities between words that do occur in the same context, like Romeo and Juliet or Alpha and Romeo, and to reduce the similarity between words like, say, Romeo and banana that don't often occur in the same context. And this brought our word vectors into the mainstream of neural nets in a huge fashion. And one of the things that isn't talked about so much that really made the field successful is some of the leading lights of the word vector fields, like Hinrich Schutzer and Marco Baroni. The first thing they did was evaluate the new models, and instead of saying not invented here, we don't like them, went around telling the rest of the word vector community, hey, update your codes, like we're doing the same sort of stuff conceptually, but the similarities are fantastic. And then in that period between 2013 and 2017, boy, things kicked off in an amazing fashion. And in 2017, Vaswani and the team from Google wrote this paper, Attention is All You Need. possibly the most famous paper in AI of the past 10 years, if not of all time, about how instead of using convolutional networks or recursive networks, they just used scale dot product attention to model the dependencies between words based on where they occur in a sequence. Now, what is scaled dot product attention? It's a bunch of projections. Not to single dimensions, but from, in this case, it was what, 256 down to 32 dimensions, or was it 512 to 64? But each of the attention modules is a projection that takes some of the words initially in a random direction, sees what similarities they have with their neighbors in these random projected subspaces, and then gradually trains the weights of those projection matrices to tell you what are the best weights for those projection matrices that get the right similarities, that get you the best predictions of what word to say next. Initially in machine translation, it was all for machine translation, but it's worked for so many things since. So here's an example that Trevor made for our book that I'll mention at the end of the talk, Large Language Models, where Juliet has a Romeo and Jenny has a, and so in the first case, Juliet has a Romeo and Jenny has it produced the token Forest. It turned out that the movie scripts for Forrest Gump, or people talking about the movie Forrest Gump, where like Forrest is Jenny's sweetheart, is the analogy that the attention head is picking out here. And you can see that partly from the strong black rectangle for the row Jenny and the column Romeo here. And then in the one on the right, all we did is added the word alpha, and Juliet has an Alfa Romeo and Jenny has a BMW, another fancy car. And what's happened along here is that the far and the alpha, it split up the tokens, the far has an even stronger pull on Romeo than the ET from Juliet token, which has already combined Juliet. And so putting alpha in between grabs the attention for Romeo to alpha, and it starts returning cars instead. Fantastic. So it's predicting the next word. It's doing disambiguation automatically, which is great. And it's using projections. No one called it quantum logic, but they didn't really need to. All they really wanted to do was predict the next words and become the biggest thing in AI perhaps ever. So, not calling it quantum logic probably doesn't bother them particularly much. I'll say one of the things that bothered me was the automatic disambiguation. Going back to the examples from the early 2000s, I was very excited to be working on developing these word spectra and understanding the meanings and the roots for them and where they came from. And then neural nets came along and said, yeah, we're just going to try and find what word comes next, and figuring out which meaning we're using. That's just all going to happen under the hood. It does, which is really good news for predicting the next word. Wasn't such great news for people who were really interested in working on ambiguity explicitly, but hey, it works. So that kind of brings us up to the present, that we've got the scale dot product attention. We've got the big AI coming online, and there's still Trevor and myself fascinated with what can we do with this and take some of the other things from quantum. So in particular, reasoning pathways, which I could talk about. But this is just around the same time that quantum computers are coming online. So in the early 2020s. And so, yeah, I'm afraid this is the unfortunate part in the talk. So, yeah, so you're doing all this great stuff at IonQ on AI. Why aren't you working there anymore? Or why aren't you working in quantum anymore? Well, because really the summary of the story is that quantum computers had this 30-year promise of what they're going to do, big computes on these very special problems, and have the misfortune to be coming online in the early 2020s where the story in the meantime has been the explosion of big data. No one really expected that in 2000, not as big as it has been, or as all-encompassing and perhaps you might say domineering as it has been. But AI has gone in a very particular dimension, and it's the opposite direction. So why is that such a big problem for quantum computers? Well, in 2020, these are not exact numbers taken from any one machine or anything, but we had about 10 working qubits. We could simulate about 30 working qubits. And there were promising ideas published for quantum advantage in machine learning saying, oh, I think if we did the same thing we did on about 10 qubits with about 50 qubits, that'd be something we wouldn't be able to do classically, or at least we can't simulate it on a classical simulation of a quantum computer. So by about 50 qubits, we should be delivering commercial quantum advantage in machine learning. Well, I thought that sounded really pretty interesting and worth working on and putting some flesh on those bones. Fast forward to 25, we have more than 50 working qubits before. And please, anyone in the room, raise your hand if you've seen any design or promise for quantum advantage in machine learning at 50 qubits. Yeah, I haven't. It keeps receding. Oh, well, maybe if we have 200 or 300 qubits, we'll deliver machine learning advantage. That, for me, working on the system, seeing one number move and what are we going to do with it not move, that was an enormous problem. And I've kept a close eye on this space, and I still see no design or promise for quantum advantage in machine learning. Why is this? It's the big data story. Start with, just take any example from today, a standard embedding matrix for a large language model, so like Llama 3. When I say an embedding matrix, we're talking about, say, 4,096 underlying dimensions, like 120,000 tokens in the vocabulary. And so anytime we project the tokens down to embedding space or multiply by the embedding matrix to take the predicted weights on the embedding matrix and then project those up to us, so which tokens are we talking about? Somehow or other, we have to have this matrix in memory. And so that's about 2 to the 29 variables. So good news for quantum computers, we could fit this in 29 qubits, fantastic. But the problem's getting the data in. And here's the core problem that boils down to quantum computers, it's the gate speeds. The 10 microsecond gate speed estimate for an ideal future quantum computer with error correction, working perfectly accurately. And I haven't seen an estimate for less than 10 microseconds. And this is very generously mainly for single qubit gates. At least the whole estimates are. That number is taken from the Herfler et al. Paper called Disentangling Hype from Reality that came out in 2023. And I was one of the people, I was working in quantum machine learning and was one of the people who took this paper very seriously and said, we've got to work on the I/O, not all the things we'd like to do if the I/O just works. And so generously, let's say we had 64 perfectly working qubits, so we only need to do 2 to the 23 ops per qubit, assuming you can do a single operation per qubit and encode a variable. Well, no, you can't. You've got to do a bunch of 2 qubit gates as well. You've got a load of connectivity as well. But even then, if you could do 1 parameter per qubit per gate operation, you'd be talking about 84 seconds or something like that, back of a napkin calculation, just to read this matrix in. And so 84 seconds is a long time in machine learning. Like, we do this thousands of times per second on GPUs. And even worse for quantum, like, whatever else we do with this encoding, we only get 64 bits out. The GPU encoding can give you any of those 2 to the 10 variables out, or any of the things you've done with them. So yeah, LLMs do these things thousands of times per second with much more direct access to the data. And the summary there that you don't hear in the press, quantum AI is small data AI. And anyone saying they're excited about quantum AI needs to explain, what are they going to do with small data AI that is genuinely commercially exciting? So, do quantum computers bring economic advantage? I think you know what my thoughts are on this. Commercially, advantage means you do something useful that someone will pay for that can't already be done more cost effectively some other way. So yeah, I do get a bit tired and frustrated when I see another article saying we found quantum advantage, which means doing something a quantum computer can do that a classical computer can't. Steady on. Like in 1999, there was a really fun experiment where they did the IP protocol transmitting messages over the internet by attaching a thumb drive to a pigeon. And they did IP carrier pigeon, IP over pigeon, and added the pigeon network to the internet. It was fantastic, but it was fun. No one said, aha, and the pigeon can do something that a classical computer can't. Well, what it can do is obvious. It can fly. But flying and delivering packets like that, no one claimed it was useful to the internet, and no one was silly enough to say, we're inventing the pigeon network or pigeon computing. But we look at pigeons and think, yeah, it's just a pigeon, seen it for ages. We hear about a quantum computer and say, that's amazing, I don't understand it. It's going to do something a classical computer can't. Well, I'll tell you, it's hard to build a classical computer, but it's a lot harder than building a pigeon. But we just don't think of them in the same way. But in terms of commercial cost effectiveness, we have to. Commercial advantage means something that can't be done more cost effectively some other way, and that is useful and that people will pay for, not just something that's novel that a classical computer can't do. So what are the options? Decryption. This is the big one that people have been excited about mathematically since 1990. There was 1995 Shor's algorithm. But decryption is a threat, not a product. And people talk about it as if it's symmetric. We need to invent it first, or someone else will invent it. No, it's a lockpick. You invent a new lock, which is what we're doing. That is post-quantum encryption. There is no, if I invent the lockpick first, I get to go around and break into everybody else's house who's updated their lock. It doesn't work like that. But go down to your hardware store and look for these products. They are not there. They are not mass market products. B, it's not a very nice thing to want to do. What a strange thing to find inspiring. The only neighborly thing to do in this context is to talk to your neighbors and say, hey, we have to all update our locks, not, hey, I'm going to buy the new lockpick and hope that my neighbors haven't changed their locks yet. Anyway, decryption is a threat, not a product. Logistics optimizations, well, they have tiny commercial headroom. It is true that a quantum computer could solve the traveling salesman problem in less time than doing factorial on a classical computer, but that's not what logistics does. Approximate solutions that get you within a hair's breadth of a perfect traveling salesman solution or a more realistic capacitated vehicle routing problem, they happen pretty quickly and get you within the headroom that, let's say, that if the traveling salesman encounters a traffic light on the way, that's bigger than the difference between a perfect solution and an approximate solution. So there is not the commercial headroom to say, oh, I'd love to spend millions of dollars on a fancier computer and spend weeks waiting for an exact solution. That's not a product. And AI, NLP, graphics, they all benefit from more data. Like goes back to this slide, there isn't a story that is at all convincing for quantum AI. The only story there is we want it. So you'll hear the science news today. AI is an enormous, expensive black box that nobody understands. Quantum computers to the rescue. If I say, please raise your hand if you've heard that story, I say, but dare say that is a different Like a lot of the room has heard that story. And the real story in science today is AI is a host of large, efficient, transparent boxes. It's only once you put all the boxes together in a massive cascade that I can tell you exactly what every box does. I can model exactly what every combination of the boxes do, and they get more and more complicated. So eventually you do sometimes get answers that it would have been really quite hard to predict. But it's not a black box. This is a myth that has been told to try and, I don't know, get some people excited about AI because it's mythical and beyond us, get a lot of people excited about replacing AI because, of course, we can do better, but it's not true. And because of that, there's no, right, AI is a host of large, efficient, transparent boxes. There is no viable proposal for a quantum computer to replace any of them. So you can't replace the whole thing if you can't replace any of it. That is very classically reductive of me, but that's how engineering works. So in science mythology, hey, we're all scientists. We deal with facts and observations. We should all accept the second column as being the facts until we see an example of a quantum computer that that can replace a classical any one of these classical boxes. And we should absolutely reject the first column because firstly, its premise is false. AI is not an enormous, expensive black box that nobody understands. That's just a disparaging myth. And for the second part, quantum computers to the rescue, there's no mechanism proposed. So yeah, I'm sad about that. I'm particularly sad because I was meant to be the person doing that quantum computers to the rescue part. So it's very easy to then hide behind, well, they've got to have someone really smart who's doing that figuring out the quantum AI stuff, who really understands AI and really understands quantum. And I'm sorry, I was meant to be that guy, and I don't do this often, but yeah, some of those people have been to Oxford, Stanford, worked at Google, Microsoft, and I failed to find an example of this working. So, if the story is there's some expert who's figured this out, so trust them. So, sorry, I was that expert and I did not succeed. So, on the bright side, the fun bit at the end of the talk, which I only have 5 minutes left for, but if we can go on a little bit, I think I will. Emmanuel, thank you. Take your kind invitation to keep talking for a bit longer than I was supposed to, and talk about what's some of the good stuff that we can still do with quantum social and economics models. Well, one of the first things we do along the way is at least explain why it is so hard for us to accept the scientific explanation on this page. So let's start with, we represent everything with state vectors. Everybody's representing everything with state vectors. So yeah, let's do that. So what are we going to represent with state vectors? Well, to begin with, individuals. The one on the right, the example is my example of two individuals, a wild dog and a tame dog. This was from a paper for the quantum interaction seminar back in, I think, about 2015, and saying that, so it's not just the wolf, the wild dog, and the tame dog, maybe it's a cute little Shih Tzu, or it's the space the dog lives in and thinks in. So it's got different skills it prizes, like running fast, or the tame dog looking cute, and an objective, getting food. For those of you that have dogs, many of them are very focused on the objective of getting food. It figures very big in there. And I don't think I'm imagining too much of a dog's mental life when I say it has a mental life, some of them, and it's not a very complicated mental life. It wants your food. And dogs, the ones that became tame, discovered that looking cute was something they could focus on, and if they focused on looking cute, they got food. They changed their point of view, or what they prized, from running fast to looking cute. And, look what yummy food some of them get. And so this can be modeled or imagined in a vector model where we have individuals' axes representing their values and mental states. And so there's a lot of work in this area. Particularly, I'll highlight the book by Jerome Bussemeyer and Peter Bruiser. It's on the second edition now. They've been doing some wonderful stuff in this area. And what's quantum about it? Some of the obvious things we see in human behavior, order effects. So this is a fairly famous one with asking people, do you think who's trustworthy? Not who's more trustworthy, Clinton or Gore, but do you think Al Gore is trustworthy, or do you think Bill Clinton is trustworthy? And you get different answers depending on what order you ask the question in. And that's how projections work. And whereas if we were representing this with intersections of sets, they're the same each time. And we can model this with qubits, a nice quantum circuit in the bottom right corner. Model this for, say, the prisoner's dilemma, where the person making the projection decision is holding the two ideas, shall I defect or shall I cooperate, in their head at the same time. And now this work has traditionally been done with one conscious observer. And so Emmanuel Porthos and I was recently talking about this and say, obviously it gets more interesting with a bigger population. And he said, steady on, what do you mean bigger population? We're talking about the psychology of individuals here. And I said, oh, well, why? Because it's the state of an individual. Well, never mind, it doesn't have to be. And actually, we started talking about, for economic applications, it can't be, or we can't do economics with just one conscious observer. So this is maybe just kind of random observation, and maybe it was a bit mystical in physics to say to get an outcome, we need a conscious observer. Well, for economics, we need at least three. We need what we call a third party. For the concept that A owns B. And we can't exchange things, transact, have money, and before we have the concept that someone owns something. And the concept that A owns X only matters if there's an alternative claim that B owns X instead. If you only had A and B, this is just a disagreement. So the concept of ownership to settle disputes requires a third party C and to settle the matter, and somehow C's belief about who owns it settles the matter for A and B. That's quite an interesting concept. I hadn't thought about it that way before. And what does quantum mechanics look like when we've got different observers? Well, here's one, not an economic example, but a perhaps simpler political example, where talking about asking people to make a decision, like go and vote. Who do you want to be the president or your representative or prime minister, whatever it is, for the next 4 or 5 years? You might have thought lots of things over the past period, but this day you have to make a decision. And that is, so you pick one, and in quantum models, that can be modeled by a projection. And now, as someone else trying to influence what goes on, you might want to pick what decision is being made. And that could be called framing an issue. And politicians do this all the time. If something on the other side is a disagreement, they will highlight the disagreement and say, I want you to canonically say what you believe on A or B. And a politician, knowing that some members of their own party will disagree on this, say, well, I'm not really an expert on that, and will refuse to commit. But if you do get people to commit, then you want to choose an axis that is going to unite your party and divide the other party. So if red's distribution is, far more up to the top and blue's distribution is over to the right, if blue can pick an issue that is nearer to over the right, then nearly all the blues are going to agree. The reds are going to be split, and the reds that disagree are going to look really, really far from the mainstream. And this is something I think we see happen a lot, and this is a good model for it. Just intuitively so far, it'd be nice to compare with more dimensions, because then you also get the order effects. Now, in these models, so in this model, we just did a random, like each point made its own random projection decision. Now, in real life, these models are influenced by their neighbors, and we can do that. That comes up in physics and quantum informatics as well. And quantum informatics, quizzics, the physics that makes you quizzical. Sorry. Anyway, Freudian slip of the tongue, but I kind of like that. But in quantum physics, there are these systems like Ising models or Ising models, where you're affected by your nearest neighbors, and there can be phase shifts where an entire region can all shift at once. And yes, we see this happening with people as well. And yeah, I hope this isn't seen as rude, but that very much explains why so many people who regard themselves as members of the scientifically interested community fully believe that AI is an inscrutable black box and that quantum computers will come to the rescue, because it's what our smart neighbors believe. And beliefs matter, and community beliefs matter. And I want to say strongly, this is not just other people. When we talk about these things, it is so easy to imagine, a rural community where people are clinging to guns and religion or something like that, one of the others. We've done a horrible job of letting social media teach us that the world is about others, and then assuming that their frailties are not our own. This is not just other people. The scientific community is really quite easily led by popularity. Sorry. There are beliefs about value, but at least that can be explained using quantum economics. So that's good news. Very briefly, there are beliefs about values, and values, I mean financial values. How much is something going to be worth in the future? And in classical economics, these are supposed to, say, come to a sort of normal distribution. So if you're using the central limit theorem, eventually, one way or another, you seem to get to a normal distribution if you're taking averages. And this doesn't happen with opinions. Some people believe that Bitcoin will be worth a ton in the end. Some people will believe it's not going to be worth anything. And indeed, this kind of talk is partly about our divergent beliefs on what will quantum artificial intelligence deliver. And most of the news is over at the right hand of the pointed diagram. My view, as you know by now, is over at the left. And when we do, so that model is a quantum walk. When we do measurements on quantum walks, it forces them to commit to have what I've called a reckoning. And the more reckonings we have, the more they collapse to the center. This happens with prices too. You don't see it with stock prices because stock transactions happen too quickly. Where we found it is the much less studied housing market. So when people, so the graphs on the right are showing the differences between offer prices, list prices, what the seller wants for the house, and offer prices, what someone offers them, and do they finally agree? And basically, when there are fewer transactions going on or more, then there are bigger differences in opinion between the buyer and the seller, or at least there is room for bigger differences. That's something that I think we could study a lot more quantitatively. And again, it's a lot harder to study the housing market. Stock trading has been much more centralized, and how traders behave has been much more modeled than how real estate agents behave, which is much more local and much more secretive in many ways. I will finish soon, I promise. So back to the very basics. So what's classical and what's quantum about finance then? What makes the housing market so different from the stock market? Well, I think it's to do with the how micro is a microtransaction? The more you can chop things up to microtransactions, the more a classical model is going to work. This goes back to, say, Leibniz. Nature doesn't make jumps, and money approximates this modulo a penny. And this was actually used, the quote, the Latin quote, natura non facit saltus, by Alfred Marshall in Principles of Economics in 1890. Then he was trying to justify the use of classical mechanics in economics. Nobody needs to justify the use of classical mechanics in economics by now. You'd be silly not to use calculus where it works. And I think we should just adopt the same approach to quantum in finance. So what's quantum about finance? Well, really important decisions cannot be interpreted. So sorry, Leibniz, nature does make jumps sometimes when we're making important decisions. So yeah, the ancient one that came to mind was the so-called Judgment of Solomon, that this baby is brought to Solomon, and two claimants are both saying, I'm the mother of this child, it's mine. And Solomon says, well, let's just cut the baby in half and give you half each. And one of the claimants says, no, don't do that, let the baby live. And Solomon says, you're obviously the real mother, it's your baby, here's your baby. So, I'd like this as a cartoon example where, no, sorry, Leibniz, in this particular case, in the case of babies, Leibniz was wrong and Solomon was right. And other things are mentioned. Transactions create recorded measurements or facts. Facts are not out there to be observed. There is a true price, and we just observed it. Negotiation, transactions makes prices. And in between transactions, all estimates of value are beliefs. Knowing that something is the true stock price, all that means is the most recently recorded one, and the chances are it's not going to have shifted too much. So I've nearly finished with some proposals and applications of so obviously I'm not going to say, my proposal is we're going to put more data on a quantum computer than a classical computer can handle, and then we're going to do the quantum Monte Carlo symbols, we're going to do that in root n speed using Grover search. We're not going to do that because even if the algorithm works once all the data's loaded, we're never going to load more data onto a quantum computer than we load onto a classical computer unless something completely changes about those gate speeds. That's the physical number I'm watching there. What we are going to see is, applications. Build the applications now, don't wait for the quantum computers. So we're likely to see more quantum effects with bigger single decisions. So look at housing where we can, rather than, for example, stock option hedging. Geometry itself, like the stuff that gave us vectors, it came to life, like the Egyptian rope stretchers in the Nile Delta, as far as we can tell, which is not very well because they apparently weren't respected very much, and their work wasn't recorded very much until the time of Euclid, and he didn't really give them very much credit. Anyway, they were going about their business literally for 2,500 years before professional mathematicians said, maybe we should pay attention to the surveyors. So let's pay attention to the surveyors. For understanding order effects in practice, work with the survey designers. My wife, Meryl, used to work for Nielsen, the ratings company, until a couple of years ago. So this conversation became not just, you should work with the survey designers, but a list of 3 or 4 people we should talk to right away. That there is expertise on this, that the quantum cognition and quantum economics decision-making could maybe be teaming up with. And applying in real estate, literally predicting what is the best offer to make next that is most likely to get you to where you want to be. The stuff Trevor and I are doing, reasoning pathways, disjunctions and superpositions, that's definitely a different talk beyond quantum economics. Machine learning for seasonal data, I think the federated transformers or rope complex time, another of the bits of quantum, bits of electrodynamics before that, using e to the minus xt or e to the xt as a exponent giving us complex time. That's exactly how rotary positional encodings work. So maybe we should be using that for encoding seasonal features in seasonal market predictions for seasonal markets like the labor market, employment market, and indeed real estate prices. There is a quantum machine learning paper in surface temperature prediction that uses not rope embeddings, but similar ideas. Again, I wouldn't go looking at those papers and say, hey, we have to run them on a quantum computer. We have to wait another 5 or 10 years and hope they actually deliver. We need to be looking at those papers and stripping out the useful parts and running them on classical computers now. There's lots of things to mine there. Conclusions, really honestly conclusions. Low liquidity brings volatility. It needs to be studied more that a lot of decisions are made in places where decisions are sparse, and we focused on the stock market where decisions are dense. But I think there's a lot to be investigated in this general rule. Low liquidity makes more uncertainty in pricing. Low liquidity brings volatility. Economic facts are social constructions. They're opinions turned into precedents. That doesn't mean they're not facts any more than Julius Caesar was assassinated in 44 BC is a fact, but it also depends on all sorts of conditions, in fact, including the probable misdating of the birth of Jesus of Nazareth to make it 44 BC. We don't know when that was, but anyway, it is a fact and a social convention. We shouldn't worry that it's not classical mechanics. Classical mechanics isn't the physics of everyday life. Of all the things I read in the newspapers regularly that strike me as even sillier than quantum computers are going to rescue AI, classical mechanics isn't the physics of everyday life. Just look at the way we compare, proving or demonstrating that a meteor struck the moon compared to estimating or predicting whether a meteor will strike the moon. We follow completely different processes. So I'm not saying classical mechanics is wrong. I'm saying it doesn't explain everything. We don't use it everywhere, and we don't have to. And we should think exactly the same way about quantum physics. Quantum theory isn't weird. Generalizations of quantum theory are all around, and we don't need to look to make them exactly literal. So they don't need to be normalized or unitary. And that's probably good for economics, because not all people care about the same concepts to the same extent. Or a lot of situations or states just don't matter to people. So they might be sort of very near the origin in this diagram. So, yeah, I've dwelt on this a bit. Quantum compute is for exact big compute. AI is for fuzzy big data. It is sad for quantum computing that after 30 years, this is the era it's coming online. Maybe in 30 more years, we'll have a completely different problems to solve, and there really will be lots of room for quantum computers there. I hope so. I loved working on quantum computers. I started off with quaternions. It's fun. It's exciting for mathematicians, but it ain't big data. And basic arithmetic is more crucial than advanced algorithms. We're so maybe not excited, maybe daunted, maybe dwarfed by quantum algorithms. I can't possibly understand them, but they tell me that they're going to make these basic back-of-the-napkin arithmetic problems go away. That's a no. If we're scientists, basic arithmetic is more crucial than advanced algorithms. You can't do one without the other. But the good news for people working on applications is quantum cakes don't need quantum ovens. So that's been the story of my career so far, and looks very much set to continue. So very excited to keep working on the applications of these quantum concepts that were running like a rocket ship on GPUs. Yeah, if you'd like to see what we're doing more inside those GPUs instead, coming back to the story, don't let yourself be told, or don't believe that AI is a black box that you can't understand. It's a whole bunch of relatively simple components that you can understand. So see inside those components, buy our book, Large Language Models, How They Work and Why They Matter. There's a website there on GitHub. That is particularly if you want to find out more about the book, or a couple of code labs there, examples, but also to file issues. If there's anything you find wrong about the book, please file an issue there. But you know, we'd love to help people just get more familiar with the really exciting stuff that's going on there, and how it relates to this basic mathematics that has so much in quantum in common with quantum physics and quantum theory. So thank you very much. I'm sorry for
Thank you,
talking
Dominic.
so long, but I
Thank
was
you.
not out of questions.